Start sharing my screen. And I'm sorry for this interruption. So thank you very much for being here today. We will talk in our seminar that this seminar is within the scope of the Montevitis project. And we will cover some aspects related to climate change impact on viticulture. And we will give viticulture as a case study, of course, on our talk. I would like to start by drawing your attention to this very important aspect of the climate emergency. As we know that nowadays we are facing significant challenges from climate change, and in fact it has been already a climate emergency because of the impacts we are experiencing in different socioeconomic sectors and in our society. We are, as I was saying, witnessing more and more frequent and intense extreme events. These extreme events can be droughts, or heat waves, wildfires, heavy rainfall, among other extreme events. And we know that nowadays, these extreme events are becoming more and more combined in what we commonly call compound events that will lead to also what is commonly called the cascading risks. Cascading risks is a very important issue in the current research in this area of climate impact science, because we know that the risks associated with heat waves, for example, can be significantly potentiated by droughts or wildfires. We know, for example, that droughts will make heat waves more likely. The probability of having a heat wave after or during a major drought is much higher than under normal conditions. We also know that wildfires are also much more likely, and their severity is clearly strengthened by the combination of droughts and heat waves. And for example, the impacts of heavy rainfall can also be significantly increased when they are followed by long drought periods, or for example, wildfires with destruction of the forests and with significant land erosion. So overall, the idea is that today the scientific community is becoming increasingly worried about these events, because they can occur together or in a relatively short period of time, which means that their risks can cascade, their risks can increase exponentially, let's say, with respect to the situations where we have only an isolated drought or an isolated high wildfire, for example. So these events are in combination very difficult to manage, for example, by the civil protection, and are also very difficult to predict. And this is then a major worry. In terms of the impact in agriculture, because Multivitis is a project more related to the agricultural sector and in particular to viticulture, we know that extreme events have been causing a lot of losses. According to the FAO from the United Nations, according to the FAO estimates for this period, this is the latest information available, but new information will come out soon. We know that there are significant losses, for example, regarding droughts, 37,000 million United States dollars of losses, floods 21,000 million, storms 19, and wildfires 1,000. So this means that in total, these events have a significant impact on agriculture worldwide. These are global figures, of course, and they will have also important impacts on food security, food quality, and in the economy in general. I would like to bring your attention particularly to droughts, because they are by far the most threatening climate extreme for the agricultural sector. And we know that in the Mediterranean basin and in Southern Europe and in the Mediterranean basin, we, as I will show you later, we will have important limitations regarding droughts and drought occurrence, not only today, in the recent past, but also in the future. And finally, a note to pests and diseases, that we cannot measure them because they are difficult to assess. But we know that pests and diseases are also becoming an issue in agriculture in general, particularly because we are having new pests and diseases in different regions owing to climate change. And we are experiencing new outbreaks also because of the phenology advancement of many of these insects and diseases, because in a warmer climate they have longer active periods. And so this is also a very important point when we talk about climate change in agriculture. In terms of the scientific evidence, well, we know that the IPCC, the Intergovernmental Panel on Climate Change, is the branch of the World Meteorological Organization and the World and the United Nations for climate change issues. They have been publishing several reports throughout the years, already over many years. The latest reports are here, the 4 latest reports. They published in 2021 the first report of this series called the Physical Science Basis. Then a second report came out in 2022, in the beginning of the year, regarding impacts, adaptation, and vulnerability. And later, much more recently, they published also the Mitigation of Climate Change report. And already this year, in 2023, and they produced the synthesis report with a summary of the main findings and the state of the art regarding climate change impacts, adaptation, and mitigation. And from this latest report, I brought here today for our discussion I brought here some basic ideas that were extracted from the text. They say that human activities, principally through emissions of greenhouse gases, have unequivocally, and this is a very important point, unequivocally means that, we are certain. We are certain that greenhouse gas emissions have caused global warming. So this is no longer a possibility, but the scientific community is already certain about that, with global surface temperature reaching 1.1 degrees Celsius above the pre-industrial level in this period. At this point, I would like to add that if we take already to the latest 3 years, we can say that the warming is already very close to 1.5 degrees. And so we are already overpassing this value and already reaching very fast the value of the Paris Agreement. Global greenhouse gas emissions in 2030 implied by nationally determined contributions, what is commonly called the NDCs, announced by October 2021, make it likely that warming will exceed 1.5 degrees during the 21st century. This is very likely because, as I said, in the previous comment, we are almost reaching this threshold, and make it harder to limit warming below 2 Celsius degrees. So we are approaching very fast all the limits that were established in the governmental negotiations. So this is a very important problem we have at the moment, particularly because these MDCs were funded, or many countries in Africa, in other less developed areas of the globe, were funded by the United Nations to develop their NDCs, the nationally determined contributions, and they delivered their reports in October 2021, but the reports showed a lack of ambition in terms of the measures to mitigate greenhouse gas emissions, and so we are not very confident about the future if we take into account these NDCs. Also, they say that deep, rapid, and sustained reductions in greenhouse gas emissions would lead to a dissonant slowdown in global warming within around 2 decades, and also to discernible changes in atmospheric composition within a few years. So I like very much this sentence, because we see that if we have not lost this war against climate change. We know that climate change is an important threat to the humanity, also to the environment, to the planet. But if we take measures, particularly if they are deep, rapid, and sustained, we can still slow down global warming, or even reverse some of this global warming, and also change the atmospheric composition just within a few years. This is very important. I would like to stress here that if we are able to slow down global warming, we will not prevent it at all. But if we can slow down the rate of warming, this is already good news. Climatic and non-climatic risks will increasingly interact, creating compound and cascading risks that are more complex and difficult to manage. We have already talked about this. Rapid and far-reaching transitions across all sectors and systems are necessary to achieve deep and sustained emission reductions and secure a livable and sustainable future for all. These system transitions involve a significant upscaling of a wide portfolio of mitigation and adaptation options. This is also very important, a wide portfolio of mitigation and adaptation options. So to face climate change, we cannot apply a single measure. We need to apply a wide portfolio of measures that can act not only in terms of mitigation of climate change, that is reduction of the emissions of greenhouse gases to the atmosphere, but also focus on adaptation strategies, because climate change is already here and we need to adapt to the ongoing changes in temperatures, precipitations, wind, radiation, and so on. So we need to focus on these two topics, either mitigation or adaptation. And by the way, there are some strategies and some practices that we can adopt that will promote not only mitigation but also adaptation, or vice versa. So there are very efficient measures that can be applied that can help us in this wide portfolio of measures. Prioritizing equity, climate justice, social justice, inclusion, and just transition processes can enable adaptation. This is also very important because we cannot adapt without agreements, international agreements, without cooperation, without promoting social justice, climate justice, inclusion. All these aspects are really, really important because the society needs to be deeply involved in responding to climate change. And ambitious mitigation actions and climate resilient development are obviously also grounded on these principles. Adaptation outcomes are enhanced by increasing support to regions and people with the highest vulnerability to climatic hazards. Sorry. Integrating climate adaptation into social protection programs improves resilience. Finance, technology, and international cooperation are critical enablers for accelerated climate action. So if we need to accelerate climate action, as the European Commission is pressing the European Union and also the whole continent to accelerate the climate transition, the climate action, we need to have, of course, the means to do that. We should bear in mind that many countries do not have the financial, technological means to overcome some bottlenecks, some constraints. So we need to overcome these limitations, these shortcomings through international cooperation, of course, and also through funding to the less developed countries. Enhancing technology innovation systems is key to accelerating the widespread adoption of technologies and practices. Enhancing international cooperation is possible through multiple channels, like, for example, international projects, scientific projects, like, for example, Montevitis and other projects. These projects will be the basis for this transition and for climate action. Now, I would like to skip to the physical basis of this problem, and I think I will not give you new information. Everyone is quite aware today that climate change and global warming are related to some changes in the atmospheric greenhouse gas. concentrations and greenhouse gas effect. On the left, in this picture, we see the solar radiation being absorbed by the climate system, the Earth system, but some of which is re-radiated as heat, for example, and the natural greenhouse gases create what is commonly called the greenhouse gas effect, that keeps some of the heat that is re-emitted again to the surface, the Earth's surface, and another part escapes to the outer space. However, when we are increasing concentrations of carbon dioxide, methane, nitrous oxide, and also CFCs, HCFCs, and other greenhouse gases, we are, of course, enhancing, strengthening the greenhouse gas effect. And in this case, if we are strengthening this effect, we are absorbing more radiation and more heat coming from the surface that is, again, remitted to the Earth's surface and will contribute to a warming, further warming of the atmosphere, with less heat escaping to the outer space. So we can say that the greenhouse gas effect is quite positive for our planet, this natural greenhouse gas. In fact, if we didn't have this natural greenhouse gas, we would have a much colder planet. It's estimated that the temperature should be 33 degrees lower than today. So it would be, our planet would be like a snowball, totally frozen. So the greenhouse gas effect is positive for life on Earth. Nonetheless, strengthened, exacerbated greenhouse gas effect like we are having today is also not good for the planet, because we are retaining too much heat and we are leading to a drift of the climate, of the Earth's climate, to a new state, or new states much warmer than life on Earth is able to cope with. And there are naturally some implications in terms of the dynamics. Here, this very simple diagram shows us how the climate engine works. It's like an engine, a thermal engine, where we have a lot of heat received in the equator, like in a thermal engine, and then the heat is transferred by circulation paths, circulation systems, towards the poles, where we have the cooling of the circulation, and the flow comes again towards the equator and goes again to the poles. And these circulation systems called cells. This one is the Adler cell. Here we have the ferrule cell, and here we have the polar cell. And these cells act as dynamos. And dynamos, as you know, when we rotate a dynamo, we produce electricity, we produce power. And this is what happens exactly in the climate system. If we are having more energy here in the equator, we will speed up and enlarge these large dynamos, these large cells, and we will have more energy available. And more energy, more kinetic energy, for example, will increase winds, will increase the strength of the cyanotic systems, and will increase the likelihood of extreme events like floods, big storms, hurricanes, and so on. So our planet is receiving more energy, and because it is receiving more energy, more energy, more potential energy is available to be converted into kinetic energy. And if we have more kinetic energy, then we are more likely to have extreme events. This is the general idea. With climate change, there is also a drift of these cells towards the poles. And we see here that these regions where we have deserts will tend to move northwards here in Europe, or polewards. And in Southern Europe, we will have a migration of these cells to the north, and we will have a decrease in precipitation as is expected. Just looking at this picture, a very simple picture, we will have that kind of transition. So we know that precipitation is very likely to decrease in the next decades as a result of climate change and global warming. We know that in the specific case of Europe, we are very dependent on the winds coming from the North Atlantic. And here we have in this picture, just to simplify, we have blue in the areas where we will have a decrease in the winds coming from the Atlantic, westerly winds. And in red, we have areas where the winds coming from the west, from North Atlantic towards Europe, will increase in their intensity. So what we will expect is an increase in the westerlies over Northern Europe and some parts of Central Europe, and a sharp decrease in Southern Europe, particularly in some areas like the Iberian Peninsula, where we will have much less westerlies, and so the winds from the North Atlantic will decrease sharply in the future. And these winds, as you know, or may know, these winds are very important for bringing precipitation and frontal systems to the whole Mediterranean basin. So the whole Mediterranean basin will tend to get drier because of the lack of these winds. And this is what we see here in terms of changes in precipitation. We will have a significant decrease in precipitation in Southern Europe and in the Mediterranean basin. Some areas will suffer more, others will suffer less, but the general trend is for a decrease in precipitation. And on the contrary, if we look at Norway and in part Sweden and Finland, but particularly Norway, will receive much more precipitation than today in the future scenario, or Greenland, or even this part of northeastern Canada, this area, and also some parts of the eastern United States. So precipitation will not decrease everywhere. Precipitation will decrease in some areas, will increase in other areas. It will depend on the region of the planet we are. But this is the picture we have for Europe, a contrast between Northern Europe and Southern Europe. In terms of historical trends, I will say that for historical trends, we have this very nice picture produced by Edward Hawkins from here from the University of Reading, and also from NOAA. And this picture is like a barcode, but shows us the colors and the evolution in the colors, with the bluish colors representing cooler periods, and the red colors warmer years. So we can see that we have quite warm years in the last few decades, record-breaking temperatures, And in 2022, the temperature has already increased 1.2 Celsius decrease with respect to the pre-industrial period here, to the beginning of the 20th century. In another similar picture, we see here that global warming is also very clear when we look at different data sets. In this picture produced by Copernicus Climate Change Service, we see that regardless of the data sets we are using, the path is very similar, and the different data sets actually converge very well. They overlap almost entirely after here the 80s, I would say 1980s, they are very coincident. They overlap significantly. So there is a rather high confidence in this warming, although we have some uncertainties here in the second half of the 19th century and the beginning of the 20th century, that is represented by this blue shading area. But overall, we can see that the temperature was quite stable until here the 20s, 30s of the 20th century, and then we started having an increase in temperatures that was particularly strong after 1980s. This was a big transition regarding global warming. If we look at another picture, very, very important picture, in this case for Europe, we see that in Europe, we are having a stronger trend. If we go backwards, we see here a warming of 1.2 Celsius degrees, around 1.2, but this is in global terms, okay? But if we look only at temperatures over Europe, we have a significant increase of more than 2 Celsius degrees. And this increase is quite evident in many areas of Europe, with increases of temperature much higher than 2 Celsius degrees, particularly in areas more in continental Europe and Eastern Europe that have been warming much faster than other areas closer to the North Atlantic. So in Europe, in fact, we have already surpassed the 1.5 degrees Celsius threshold and even the 2 degrees Celsius threshold for global warming. This is another map that shows us what I was saying before. We have some areas in Europe that have been warming much faster. These temperatures are changes per decade, but only starting in 1960 and ending in 2018. In any case, we see that some areas of Europe have been warming very fast, and also in this area, for example, of the Middle East, where we have very, very significant warming, significant upward trends in temperature. This region has been warming very fast, actually. Precipitation is another thing, another very different pattern. Although this pattern ends in 2015, we still can see that in terms of annual precipitation, there's a left panel, we have decreases over most of Southern Europe, but also decreases in other areas of Central Europe. and particularly here in this area of Western Iberia and Portugal, the decrease in precipitation has been very, very deep, very significant. In Montenegro, the decrease in precipitation has also been observed, but it's not so dramatic, I would say. On the other hand, we have Norway with an increase, already an historical trend for an increase in precipitation. So this is in line with what I told you before regarding the Adlai cell, the movement of the Adlai cell and to the north, and the decrease in the westerlies over Southern Europe, and an increase in the strength of the westerlies over Northern Europe. In summer, the picture is a bit different, but not so different. So Southern Europe and Central Europe will have been having a decrease in precipitation. We see here significant decreases in Hungary, in Slovakia, in other countries in this area, and also in the Alps. So precipitation has been decreasing significantly over all these areas of Southern Central Europe, and increasing again in Scandinavia and parts of the British Isles. This picture produced recently in the sixth assessment report of the IPCC that I presented at the very beginning of this talk, shows us the planet. This is a schematic diagram of our planet. Here is Europe, Africa, South America, North America, Australia, and Asia. Just for your reference, here is India, here is China, here is the United States and Canada, and here we have Europe, the Mediterranean, Europe, Western Europe, Eastern Europe, and Northern Europe. And we see that we will have, based on trends recorded throughout the planet, we are quite confident, with high confidence, with these three circles. In many, many regions worldwide, in Europe, it's evident. In all regions of Europe, we have high confidence for an increase in temperatures, particularly in hot extremes like heat waves. So heat waves have been increasing very significantly since the 50s. These trends are computed since the 50s until roughly the present time. And so we see that heat waves, hot extremes have been increasing very, very, very significantly. If we look at heavy precipitation events, in this case, the picture is different. We see that for Northern Europe, there has been high confidence for a strong increase in heavy precipitation events, extremes in precipitation. In Northern Europe, in Western and Eastern Europe, there is some increase and some confidence in the increase, while in Southern Europe, in the Mediterranean basin, there is low agreement. So there is low or limited confidence in a change in the extreme events. So we cannot say that extremes are increasing, precipitation extremes are increasing in Southern Europe. This is not a clear idea. So some studies show in some regions an increase, other studies show a decrease, so there is no consensus, and the trends are typically also very weak. We don't have a clear picture for the Mediterranean today. But for the Mediterranean, we have, in fact, a problem that is here highlighted in this picture. Here we have a clear increase with a medium confidence. It's not a high confidence, but we have a medium confidence for an increase in agricultural and ecological droughts. This is a much more complex phenomenon. So we need to study it much deeper. But in any case, we can say that the Mediterranean and also Western North America, particularly California, are the regions where an increase in droughts have been more pronounced in the last decades. So these two regions are the most threatened regions regarding droughts in the whole planet. And for 2022, we had some record-breaking situations. We had, for example, here we see that these red areas were the warmest on record regarding the average temperature in 2022. Also much warmer than average, or warmer than average in most of Europe, almost everywhere, I would say. And so 2022 was an exceptionally warm year, particularly over some Western Europe. Now looking at the summer, now is summer. The summer of 2022 was also extremely dry. So we had records of being the driest summer on record in these areas, with dark brown, light brown, much drier than average, in other areas with brown, also dry. So almost everywhere, with some exceptions like in Greece or Sicily or Norway or Iceland, we had a summer that was actually very dry in most of Europe. And so we had a kind of compound event because we combined these dryness areas with very warm temperatures. So it was a very warm year, but also with exceptionally dry conditions throughout Europe. This can also be illustrated by the river flows in Europe. In brown, we see rivers with exceptionally low or notably low flow, and we see major rivers in not only in Southern Europe, but also in Central and even in Northern Europe, with flow rates significantly lower than average. And here we have the Danube, for example, and also many other very important rivers in Europe with river flows much lower than the average. So just to keep this record, and for last September, because in October is still on the way, and we don't have final data for October, but looking at the last September, we also see that the last September was the warmest September on record. This time series is only for the September months from 1850, and we can have an idea that the last September was really an exceptionally warm month. It was by far the warmest September since we have records in terms of global means, not for Europe, but globally. So the last weeks were really much warmer than it's normal. Here in Portugal, for example, the first half of October, and also in many areas of Europe, was also very warm, with temperatures, record-breaking temperatures during several days in a row. So we are really facing a significant warming in these few last years. Another very interesting picture from the Climate Change Service is this one, where we see the 30 warmest months on record globally. And we see that in 2023, that has not ended yet, but we have already several months of this year that are already in the ranking of the warmest months globally. The warmest months globally was July of this year, August of this year. So this summer was jointly, July and August, the warmest summer on record, so even worse than in 2022. June 2023 was also among the warmest months on record globally. And September 2023, as we have seen in the previous picture, is also here already among the 30 warmest months on record globally. And we have to bear in mind that these are global mean temperatures, and in these months, the southern hemisphere was in winter. So it was not, these months are not summer months everywhere. They are also, July and August are also winter months in the southern hemisphere. And another very interesting picture from the Climate Change Service, and I brought a couple of pictures from their service because I think they are really doing a great job. They are currently the best platform to access climate data and climate information. So please visit this platform, and I will talk about that later as well. And if we extrapolate just linearly the warming of the last years, we see that we will reach the 1.5 degrees Celsius warming in September 2034. So we are already very close to reaching that threshold that we would like to use as an upper boundary until the end of this century, of the 21st century. Now I move to the future and to the climate projections. And for climate projections, we usually, we don't know. We have been talking until now regarding historical trends, data collected by weather stations worldwide. But for the future, we need to have climate models. And for climate models, we have to model our climate using different strategies, but the main idea is that we have to put our planet within a computer. So we have to cover the whole planet, the whole planet with grid boxes, and for each grid box we have to parameterize all the processes, all the important processes, like, for example, heat and radiative transfer, clouds, the water cycle, the carbon cycle, the ocean, the rivers, the snow, the mountains, the orography, the land cover, the vegetation, all the biosphere, atmosphere, processes. Well, in the end, we have a large set, a very large set of fluxes of mass, heat, and momentum between the different components of the climate system, and we have to model all of them. To have a good climate model, we have to model everything. So climate modeling is a huge exercise that requires hundreds of people working on a daily basis to develop a climate model. So a climate model is not something that runs in Excel or in our own laptop or computer. Climate models do need huge computational resources, high-performing computers, and take a lot of time to develop, because they need to integrate all these processes and parameterizations in the model. Otherwise, we will not get a realistic picture of our planet. But climate modeling, as I said, is very time-consuming and requires high computational efforts. So typically, we have a grid covering the whole planet that is relatively coarse. And this grid, this coarse grid, is not in many cases enough to resolve all the processes that we have to resolve, like, for example, in agriculture. If we look at this grid here, we see that in Portugal, we have only 3 grid boxes. Or if we look at Montenegro, we have just 1 grid box that cover the whole country. So we don't have enough detail from these global climate models or global circulation models. We don't have enough detail for an accurate assessment of the impacts of climate change on a given sector. So we need to couple in these climate models, or to nest in these climate models, other models that are similar but will run in limited areas. This is why they are called limited area models, or regional climate models, because they will cover only a sector of our globe, and in that case, we can increase the spatial resolution of the grid that we cannot do in the global model, because we don't have enough computational resources for such a fine-scale grid running globally. And then we, in some cases, have, besides the global model, the regional model, we have to develop, like, for example, statistical downscaling approaches to increase the spatial resolution even further, to realistically capture the mesoclimatic and microclimatic conditions of a given region or location. And so this is the chain, the model chains we commonly use in climate research. To know the projections, we also need to follow different pathways for the greenhouse gas emissions scenarios. We have different greenhouse gas emissions. These are the newest SSPs, shared socioeconomic pathways. And they show, for example, this one, SSP5, is the worst, where we have a continued increase in the emissions of greenhouse gases, in this case carbon dioxide, until almost the end of this century, with a sharp increase here throughout most of the 21st century. In SSP3, we have also an increase, but the increase is more sustainable, is much weaker, the upward trend. And in turn, we have the other scenarios like SSP2, which will have an increase and then a stabilization by 2050, and then afterwards a decrease until the end of the century. And we have also the SSP1 scenarios, where we have a decrease in the greenhouse gas emissions right from the present until the end of the 21st century. Similar considerations can be made for other greenhouse gases, like, for example, for methane, nitrous oxide, or other sulfur dioxide here, as we see. And based on these different pathways of socioeconomic development and greenhouse gas emissions, we will have changes in the greenhouse gas concentrations, and we will have corresponding changes in the global temperature that can reach a range of values from around 4 or 5 degrees. The change in global mean temperature is here very close to 5 degrees until the end of the century, 4 degrees for the SSP3, and then we have 2.5 for SSP2. So even SSP2, this scenario where we have an inversion in the emissions, will not be enough to limit the global warming to the 2 Celsius degrees warming, as we see here. And we have also the SSP1 scenarios, and these scenarios will effectively limit our warming following the Paris Agreement. But they are very unlikely from my own viewpoint, because it's very unlikely, taking into account the current socioeconomic situation worldwide. It's very unlikely that we will have a decrease in the emissions from now on. In fact, we are experiencing an increase in the greenhouse gas emissions and a sharp increase in their emissions still today. So we are more likely to go over these 2 paths, SSP3 or SSP5, maybe SSP3. So in my perspective, we should expect a warming around 4 Celsius degrees until the end of the century, taking into account the current status. This is the most likely situation. And if we look at the world 4 degrees Celsius warmer than today, this will be the changes. So we will have areas of the planet with very warm temperatures. As you see, we will have in areas of Europe increases of temperature of 6 Celsius degrees and 7 Celsius degrees in the Arctic, which will imply the melting of many of the ice sheets in the Arctic, also in the Antarctica. Some important dryness, very significant drying trends in the Mediterranean basin, and some increase in extreme precipitation worldwide, but the Mediterranean basin will not suffer much from this increase. For Europe, we then have climate change projections for mean temperature and for annual precipitation. For mean temperature, we see an increase everywhere, particularly in Eastern Europe and Northern Europe. And for precipitation, we also can identify the 2 sides of this trend, with wetting over Northern Europe and drying trends over Southern. The extreme events will be also, as I said, more likely in some parts of Europe, particularly in Central and Eastern and Northern Europe, less frequent in Southern Europe. For example, in summer, they will be less frequent than they are today. So this is an open debate, but for the Mediterranean basin, we are not quite sure about the trends of the extreme events, but the general trend is for no significant changes or even slight decreases in the frequency of occurrence. droughts will become more frequent in the future. And I will now jump to the next part of the talk regarding an example for the Iberian agriculture in climate change. And I brought this example. You are not in the Iberian Peninsula, but I think this example can be extrapolated to other areas of Europe, of Southern Europe particularly, and to Montenegro as well. And we see here, based on a very simple index, the Demartoni aridity index, we see that the Iberian Peninsula will become drier in the future. The font size is very small, but you can see that we are moving from this situation today towards, let's say, this situation where we have much more aridity in this area of the Iberian Peninsula, and a general increase in aridity everywhere. And if we look at the land use changes in water use, we see that for these hydrological basins or watersheds, we see for some of them significant increases in the irrigated areas. The irrigated areas are in green. And we see here, for example, for the Tagus basin, we see an increase from a relatively small value to around 25% of the land area devoted to agriculture being irrigated in 2019. So this is an evolution from 2000 to 2019, which means that we are increasing very significantly, very rapidly, the irrigated areas. This is, on one side, stimulated, fostered by climate change, because the climate is becoming drier and warmer, so we need to irrigate more the crops. But on the other side, we are moving on the wrong direction, because we are having, in the future, we will have less water available for irrigation and for agriculture in general. And we are increasing at the same time the irrigated areas. So this is something that we should keep in mind, that we are adapting to climate change, but at the same time we are in a trajectory that is not sustainable in the long-term future. And these are some ideas for the increase in aridity and soil moisture that do confirm that the Iberian Peninsula will become much drier with less water available for the future. Maybe I will now stop just to ask if you have any question, because the next we are going to move to the second part of this talk, and I will give the floor to Elder Fraga. But before I give the floor to Elder Fraga, I would like to know if someone would like to ask some question, some comment.
Maybe I can say something. I don't know if you can hear me.
Yes, yeah.
I didn't watch the whole presentation because I was absent the first half, but I would like to say that the presentation was very interesting, and I loved how you explained everything about climate change, and it was interesting for agriculture too. And I would maybe like to ask you, for agriculture, are there any specific examples of maybe climate-friendly farming techniques that you know of, or that are, I don't know, used maybe?
Yes, there are some very good examples that we can discuss that later. Maybe it's better after Elder's presentation, because And then the next part, we will focus more on agriculture and on viticulture, and Elder will already talk about some adaptation measures that are more sustainable. And so
Okay.
we can discuss that later on after Elder's presentation, if you don't mind. But
Okay. Thank you.
thank you very much. So if there are no other questions, maybe Elder, you can share the screen. Thank you.
Okay, thank you. I think I'm already sharing. Okay, so we try to understand a little bit about how the climate system works and what are we expecting from climate change. And we can come to a conclusion that we are expecting higher temperatures in Southern Europe and increased droughts, less precipitation. So I will now try to explain a little bit how these factors, as well as others, will impact viticulture as we know it. So this is a map from the main winemaking regions of the world. And you can see something very curious here is that although there are other regions in the world that have potential for viticulture, the main winemaking regions in the world are very narrowly located if we look at the global map. And roughly they are located in the northern hemisphere between 30 and 55 degrees, and in the southern hemisphere between 25 and 45, more or less. So we know something that these factors and these locations is not a coincidence. This is tied to the climatic characteristics. So if this is tied to the climatic characteristics, we know for a fact that if climate change has an impact on these regions, it will surely have an impact on the wines produced here. So a little bit of statistics. This shows that, for example, in Europe, it has about 65% of the winemaking regions of the world, while in the American continent there are 20%, and in the other continents they are roughly 5%. And I'm talking about just wine, because there are a large increase in countries that produce grapes for food consumption, table grapes and raisins, particularly in Brazil and in China. And especially in China, there has been an increase in production of grapes, in table grapes. Nonetheless, these grapes lack the quality to produce high quality wines. So we are focusing here on the production of wine, not just in the production of table grapes. And for the production of wine, we know there are three main factors that have a very big impact on the wine quality and on the wine production, productivity, etc. And these factors, we can discuss that the soil has a very large role. For example, the soil texture, the soil depth, the availability of water and nutrients from the soil, the cultural decisions, the decisions and the management that the farmer does, such as the vine intensity, the selection of the cyan and rootstock, the fertilization, the irrigation, the pest control, the type of pruning, and other factors also have a very, very large role. But we can see here that there is one factor that changes from one year to the other, or even from one season to the other. It is the climate, the climatic factor. And these three factors are very important, but I would say that the climate has a critical role. For example, the temperature is very important for the phenological for the development of the plant, of the grapevine, not just for the grapevine, for all plants. Temperature is a crucial factor. Other factors like solar radiation, humidity, precipitation, wind, evaporation are also important factors. And all these factors, these three factors combined, they represent something that is called in the viticultural circle as the terroir. I'm not sure everyone is familiar with this term, but the terroir is like it represents the brand of the wine. So the soil, the climate, and the cultural practices go into this brand. And all these factors, obviously, they have important roles on, for example, on the vine vigor, on the foliage characteristics, on the canopy microclimate, of course, which will ultimately result in changes to the vine physiology and fruit composition. And of course, we here have to include the enological practices, which will, all of this will affect the final quality of the wines. But I talked a little bit about the climate, and we're talking here about climate change. So we must understand what is the importance of the climatic factor. For example, for this graph that I show here represents the development of a grapevine through the growing cycle, through a year, from the winter until it reaches the next winter. So as you can see here, the vine starts to grow. It reaches certain phenological stages, such as the flowering, such as the veraison, and finally the harvest and the leaf fall, and it goes into dormancy. And there is one very important factor that controls this, and I already talked a little bit about this, and it's temperature. And it is very well known that temperatures above 10 degrees control the development of the grapevine. So, for example, in a country that doesn't have temperatures above 10 degrees, cannot sustain viticultural production, while other countries that temperature will not go below 10 degrees throughout all of the year will also have problems if they want to grow, if we want to establish viticulture. Also, temperature is very important for wine quality. In countries that are very cold, it can lead to problems with sugar content, and obviously this, if the sugar content is not too high, will also affect alcohol content, and this will bring problems to aroma and balance. On the other hand, if the conditions are too warm, the sugar content will go very high, which will lead to extremely high levels of alcohol, which will also bring other problems regarding the aroma of wines and balance. And of course, there is an optimum. And this optimum is not a rigid factor. We cannot just establish what is the optimum regarding specific values, because this we must consider the grapevine variety that we are transforming into wine and several other factors. But there is an optimum threshold in which we can safely say that the conditions, the climatic and temperature conditions, will obviously produce high quality wines. So I will show you again the main wine regions of the world. And if we take a look at the temperature conditions in which these regions have, we can say that in the growing season, all of these regions have more or less 12 to 22 degrees Celsius within the growing season, of course. So if in the future climates we are expecting temperatures to increase, what should we expect from these ranges, both in the northern and in the southern hemisphere? If the temperatures are expected to go higher, this should lead to an expansion, a northern expansion towards the North Pole in the northern hemisphere and towards the South Pole in the southern hemisphere. So you can see now that this is expected to lead to problems, particularly in these regions that are already in the near the limits of the suitability for viticultural growth. So in the winemaking sector, there are some factors that we need to study. So we should study the grapevine sensitivity to environmental factor demands for a better monitoring and prediction, both in the long and in the short and the long term, promoting a better management and potentiating efficiency and sustainability gains. So our motivations are to assess the climate suitability for viticulture, the suitability for high quality wine production, the wine quality and berry attributes, the phenology. Phenology, for those who doesn't know, are the stages of development of certain plants, which can include, for example, the flowering stage, the bud burst stage, amongst others, and to study physiological parameters of the grapevine. All of these are all studies that we should take into account the regional and local climate change impacts. And we have another goal is to, after we study the climate change impacts on these specific attributes of the viticultural sector, we should and we try to develop specific adaptation and mitigation measures, and to provide with stakeholders and decision makers guidelines for them to adapt to the climate change. So, for example, in one of our studies, what we did was we tried to assess what would be the yields for the past and what would be the changes in the yields for the future, using both climate models to provide climatic data and crop models that study the effect and the development of the grapevine. And what you can see here on this left map is the grapevine yield as it was provided by the models for the recent past period, 1980 to 2005. This is our study. This was our study period. And what I can say here is, for example, for regions in Southern Europe, the yields tend to be lower, and we know this is true. So we know that the model, it provides, of course, not 100% valid results, but if we look at the patterns, we can understand that the model is actually providing good agreement with what we know is true. And if we feed the model some data from the future climate, regional climate models, we can then extrapolate what will be the differences between the future and the past. And this is exactly what this map here shows. It's a difference. That is why it is in a blue and red scale with positive and negative. It's a difference between what we have what we'll have in the future and what we have now. And what you can see is there is two totally different results. These red regions, what you can see that are mostly under Mediterranean climates and Southern Europe, will have lower yields, which will be very intense, particularly on the inner south on the south inner Iberia, some regions of Italy, Greece, amongst others. while mostly in the central and northern part of Europe, we are expected to have higher yields. Also, this map shows what other regions in the future will have suitability for viticulture. If we compare the patterns for the future and for the present, you can see that the patterns for the present limit viticulture around the parallel 59 degrees north, while in the future there's probably going to be an expansion of the suitable conditions for viticulture above this parallel. Well, these results come from several factors, and one of the factors is the enhanced water stress. As you can see in this map, this shows that in the future there's going to be an increased water stress, but this will lead some regions to be more adapted or less adapted depending on the conditions that they will have today. For example, some regions may have today an excessive amount of precipitation, while the decrease in precipitation may be useful for viticulture. Some of the things that you should know is that the plant itself doesn't require a lot of precipitation, and sometimes excessive precipitation may be bad for wine quality. So this the decrease in precipitation may have positive factors for some regions and negative factors for others. Regarding phenology, for example, what I have here is the date of flowering, for example. And what you can see for the past is the date of flowering is reached sooner in some regions in Iberia and some regions in southern Italy, for example. These patterns of blue, while the patterns of yellow and red indicates that the plant reaches flowering at a later stage. Well, for the future, the increase in precipitation will lead towards earlier phenological events and earlier flowering. So you can see now that this will have impact on the flowering date, and if it has impact on the flowering date, it will possibly repercute on some of the management conditions. The farmer will need to align his calendar differently than they have been doing in the past. Well, I show now some other results, but mostly for Portugal. As you know, Portugal it extends through some latitudes, so it has two different types. Although it has a Mediterranean type of climate, it has a northern part, which is more humid, and a southern part, which is more dry, which you can see in these maps. So we calculated some bioclimatic indices that translate into certain characteristics of the grapevine. For example, this is the Uglin index that shows the maturation capacity of a certain region. And it shows us that, for example, in northern Portugal, the varieties that are that don't require so much thermal accumulation, they should be more suitable for these regions, while the southern part, which is much warmer, the varieties that require more heat are particularly suitable for these areas. Also, if you look at this central map here, this is the dryness index that shows that also the country is divided in two different sectors, three actually, if you count this blue part, regarding dryness. In the southern part of the country, it already shows moderate dryness in this period. The northern part of the country already shows some humid characteristics, particularly in this part in blue right here. And also in this right panel here, I show the hydrothermal index that shows the potential for the risk of plagues, of pests and diseases, especially downy mildew disease, which you probably know. If we now show maps for the future, and I am changing to the maps from the future, you can see that, for example, the increase in thermal accumulation in the Uglin index is very visible throughout all of the country, but particularly in the southern part of the country. It already expands through the top part of the scale, reaching values that are above 3000 degrees throughout the growing season, which only can be found today in tropical locations. Okay, if we move now to the dryness index, you can see the appearance of this area here that shows a red pattern, and this red pattern indicates that viticulture could not be established without access to supplemental irrigation. And we know this actually because these maps here and these projections here, I'll go back, were made until the year of 2000, and we know this is true over the last 2 decades. We know that there has been a very large investment in irrigation in this area. And also this last map here on the right shows actually a decrease in the risk for the downy mildew disease due to less precipitation and less humidity, which does not mean that the appearance of new diseases cannot be possible. Well, these maps here just show thermal accumulations for the region, which shows another index that has that translates into particular characteristics of the grapevine. This is the growing degree hour index. And you can see here, this index has a very strong particularity that it translates better into what the plant really does than the previous Uglin index that I showed in the last slide. Because at some levels of extreme temperatures, this index stops accumulation. So this is why actually in the most hot areas of Portugal, there is a decrease in accumulation of this index. Well, this also brings us to a very important factor, because when temperatures are too high, plants stop responding. So when I said before that we should expect earlier phenological events, we should also take into account that if temperatures go above a certain limit, we may not reach the development stages, because simply the plants will stop responding to the temperature and will just not advance their phenological development. Another important factor is the chilling. And this index shows the chilling portions. You probably heard of the chilling hours. The chilling portions is just an advancement over that chilling hour concept. Is the accumulation of low temperatures, which are needed for the dormancy stage of the grapevine. The grapevine is not a very demanding plant in terms of cold temperatures, but it still requires some cold temperatures to complete its cycle. And if temperatures are going to increase in the future, we should expect less chilling in the future. And this is obviously what this map shows. This map here on the left is the present, the past, and the difference. And you can see here in the difference map a very strong decrease in chilling conditions for the future, which should also impact the dormancy stage of the grapevine. Well, What I show here now is the combination of two indices, the ugly and the dryness index, and throughout the wine regions in Portugal. We have several wine regions. One of the most important one is located in the north, is the Douro region, where the port wine is made. And for these regions, you can see here for the future, particularly in the last period, 2071 to 2100, over the very severe scenario, that this region, the Douro region, will be very impacted, both in terms of temperature, will reach areas which is too hot, and also in terms of drought, where it will reach the level of excessively dry. One other thing that is very important to discuss is the exposure to extreme events. And on these maps here on the left, it is shown the cumulative dry days and cumulative wet days, which is kind of an opposite index. And you can see here that there is going to be a strong increase from this map here on the left, which is the present, until the future in terms of cumulative dry days, while cumulative wet days is expected to decrease a little bit. On this index here that I show on the top right, it's called the tropical night. Yes. And here you can see that, for example, for the Douro region, we're expected a lot more high temperatures during the night. And on the bottom here, in this bottom panel here, this is the heat wave index. And you can see here, while in the past we had, for example, less than 20 days heat waves, while in the future this is going to be a lot more heat waves, particularly over the south, the southern Portugal, and some regions here, for example, in the coasts. Well, somebody asked what can we do in terms of adaptation measures and some strategies that we can. And actually, one of the strategies that when I was in Montenegro, I saw that you already apply is irrigation. And for example, we did this study for Portugal, and these two maps here, they just show what is going to happen in terms of grapevine yield if we don't irrigate, and if we irrigate, but not completely random irrigation. Of course, it has to be a controlled irrigation, drip irrigation, only when the plant requires water. And this shows here that if we don't irrigate, if we don't apply any adaptation strategy, we're going to have strong yield losses, particularly in the inner part of the country. You can see here in the Douro, where we are expecting a yield decrease down to 60%. While if we apply just the right amount of supplemental irrigation, we can keep the yield, the future yield, within current levels. Another adaptation strategy is the varietal selection. And what we did here is we try to analyze where the varieties have their optimal suitability and their optimal conditions for growth, both in the present and in the future climates. And we come to an agreement that while if we study what are the varieties that are best suited for the future warming, we can find out how to adapt to these scenarios. Well, I'm going to give the floor back to Professor João Santos. He's going to talk a little bit about the previous project we had, and he's going to continue his part on climate. Thank you.
Okay, thank you, Elder. So, continuing this presentation, and we are coming to the end of our seminar today. I would like just to mention that before Montevitis, we had already another project called Clean for Vitis. It already ended last year, but we still have some important information that was produced within this project. As a matter of fact, the team remains the same, with the exception of the colleagues from UDG that joined us in Montevitis. And we have produced a white paper on viticulture and climate change in Europe. I suggest that you go to the website and download that document. And there is also a video that you can follow. And it's a very interesting video that you can also find in YouTube about the adaptation measures for viticulture. Today, I also brought here one suggestion for doing yourself some exercises on climate change. I will put on the chat a document. Just one moment. I will put, as I was saying, on the chat a document that you can use. In that practical exercise, I will send it to everyone in the meeting. It's a PDF file called Guidelines. Okay, and you can download it, and in that document you can find some instructions. I will stop sharing and sharing again. You will see some instructions on some instructions on to produce some climate information. The goal is to get to this picture that is in the very end of the guidelines. If you go to the last page, you will find an example of a picture that you can produce by yourself, each one of you. So it's a very simple exercise, but it will take some time because you will need to install software and you will need to do some procedures. But after accomplishing this, you will be able to produce other pictures like this for other regions in the world. You can focus only on Montenegro. You can also choose other variables. So I think it's a very useful exercise. If you have questions, of course, I can try to help you. It's not so easy because we are working remotely, but I can try to help you if you have any kind of question. Of course, we will not have time to do this exercise today because, as I said, it will require, first of all, software installation. This is the first block. So you have, first of all, to install in your laptop. You can use your own laptops. It will not require much space. And you should install this Java development kit 21 or later. Then you can download from this link the Panoply, NASA Panoply, which is a very useful software for visualization of data. You see here the website. It's very nice, and you can open data sets, large data sets, climate data sets using this software. If you go to the downloads, you see they have here instructions to install Java. This is why you need to have a good Java version. And then you have here download Panoply to choose the version of Panoply you want. For example, if you are working in Windows, you can use this link, and you will automatically download a zipped folder. And the installation is pretty simple. You just need to drag and drop or unzip the folder, and the program is ready to run. So it's very, very easy. Another software that is useful for this kind of applications is Cygwin. Cygwin is a platform that emulates on a Windows operating system, emulates a Linux environment. So if you go to the website, to this website, you will have also the installation for Cygwin. You have here the installation files, so you can install the software in your computer. And in the installation, you should select packages. When you are asked to select packages, you should choose the installation of CDOs, these climate data operators, that will be installed within the Cygwin installation. Then you will also need to install QGIS. I think maybe you are already familiar with QGIS. It's the alternative, the open source version of ArcGIS. It's very useful for students because you don't need to have a license, a paid license. So it's very, very practical, and I recommend you to download and install as well in your computer. So this would be the first step to install everything. This software, it's not very much. You can just do that in 1 hour or so and have your computer ready for the next steps. And for the analysis, you can go to the Copernicus website. I think I have already stressed several times in my talk that Copernicus is an excellent platform with information for the whole world, not only for Europe, even though they say that they are Europeans' eyes on Earth, but they have, in fact, data for everywhere in the world, and they are the best platform with climate data. And here you can scroll down and see a lot of information regarding, for example, these main thematics: atmosphere, marine sciences, land, climate change, security, and emergency. They have also hubs like the Health Hub, the Coastal Hub. So this is, I would say, an endless a source of information. Climate change, particularly, is one of the most important parts of this platform. Here you can see the latest reports, for example, the European State of Climate 2022. These reports have been widely disseminated in the media, on the TVs, on the radio, everywhere in Europe. They are being very famous because in each year they produce the report of the last year, and this has been broadcast intensively. Here you can see the climate data store, where you can find out a lot of data. And if you write here, for example, agroclimatic, you will have access to a huge number of data. For example, agroclimatic indicators for the whole world. And here you have a description of the data. You have a description of the variables, the data sets, the spatial resolution, the time resolution, the variables, the formats. And here you can download the data using, for example, selecting biologically effective degree days. You can select the model you want to analyze. And you can select the period. In this case, it's just historical periods, because we are only considering reanalysis data, which is an observational data set. And you can take the data in a zip file and download the data to your computer. So this is the exercise. Here you can extract the data, download it, and you just need to follow every step here. Repeat the procedures and download the data. Then you can visualize the data. I can give you very shortly one example. This is one file. These files, by the way, are .NET-C, because their format is NetCDF. You cannot open them in regular programs because they have all the data compacted in binary formats. But in Panoply, you can easily visualize the data. And here you have data for the whole world, and you can jump the days. See, so we are moving from the 11th of May 1981, and we are moving, as you see, we have a progression of data. So this software is quite useful to visualize the data. Another part is to extract data in data mining. Here, there are some examples that you can run in Ciguin, in the Ciguin console. Here, you can select a latitude and longitude box. In this case, I selected latitudes and longitudes for Europe, for the whole continent. You can compute sums, annual sums or year sums using this command, and the climate means using this command. Then you will get a series of files like here, and you can get a file like this one that I will open in Panoply. And now you see that we have already only Europe, the data only for Europe, and the data is averaged from 1981 to 2011. So we can do that with the CDOs, those commands, and do some data mining and extract data for us. Then after having this data, you can just drag and drop. For example, you can drag and drop a shapefile with countries, and then you can drag and drop to QGIS. This is QGIS, and in QGIS you can drop the file directly to QGIS and select the raster, and here is the raster already for Europe. So you have already here a preliminary map of Europe that you can work on it, of course. You can work on the properties, and you can choose different color scales. You can choose different applications, as you see, and then you can produce a figure that you can export by selecting here. I'm sorry, I'm going very fast, but the idea is that you can explore by yourself. And here you have already the canvas with a figure, and here with these buttons you can add captions, you can add many details like the scale and many other the frameworks and many other elements to your map until you get a map similar to the one that is shown here below. So this will take you some time, but for those who are keen on learning more about data management and this kind of things, this could be a good exercise to do. And please let me know if you have any kind of question that you would like to clarify. And I don't know if you have more questions, maybe for Elder, before we end.
Maybe not.
Maybe
Not this time.
So-
Okay, then I just wish to say thank you for these inspiring presentations and valuable insights into important themes we cannot neglect these days in our daily lives. So Joao, especially thank you for tips related to the software installations. They are really especially useful for our students. We will encourage them to access the links, download the software, and explore in more details that manual you are going to send, or you already sent on chat. So I believe on that way they are going to be let's say, prepared for our next meetings and our next webinars of this kind. Thank you very much.
Thank you.
Thank you.
So see you.
Thank you.
See you. Bye.
Thank you. And I suppose
Thank
that they
you.
will contact Antonio for some details, our research students.
Yeah.
I suppose so.
Yes.
But we
Yeah,
don't have time. Okay. Thank you so much again.
Thank you very much.
Thank you.
Bye. Bye.
See you
Bye.
again.